All right, 2024 AP Calculus BC free response questions. Let's take a look at these. So we're going to start off, I guess, Part A, Section 2, Part A, which is FRQ, free response questions. Time 30 minutes, 2 questions. So we need a graphing calculator for these portions, okay? So we get 15 minutes for a question. All right, I'll probably take longer than that just because I don't want to go that fast. And I'll make fewer mistakes and ideally be more understandable. So we have some data. The temperature of coffee in a cup is modeled by a decreasing differentiable function C. So yes, it looks like the temperature, that's warm coffee, that's like boiling. Starts warm, gets less warm after 12 minutes. For C is measured in degrees, for 0 less than 12, table above. Okay, approximate C prime of T using the average value 3 to 7. So the work leads to the answer. All right, so for this, I'm going to start by drawing a graph. You don't have to draw a graph. I'm going to draw a graph because that's how I think. So here's going to be T equals 0. We'll have 3. We'll have 7. We'll have 12. Not drawn to scale. We want to find C prime of 5. And they told us to use, I think, average rate of change. So average rate of change basically means that we draw a line, something better contrast, from 3 to 7. So this axis is time. This one is temperature as a function of time. You just want to find the slope of that. And to do that, we're going to do dC of t. So I'll do it. So this is dy dx. Change in y over change of x. That is going to be the slope. To adapt this to our particular case, we're going to say there's going to be change in C of t over t. So this is going to be temperature, which is 69 minus 85, all over 7 minus 3. 85 minus 69, I'm going to go to Wolfram. I know you don't have access to Wolfram when you are taking an AP exam, but I do. So I'm going to use it. So we have negative 16 over 4. That gives us negative 4 degrees Celsius per, I think it's minute, but I should probably check. Maybe it's hours. Nope, minutes. So the answer for A would be negative 4 degrees Celsius per minute. And that's going to be our approximation of C prime of 5. And what I did there, so I basically looked at 3 and 7, both on the side of 5, and then found the slope between them. And they tell us specifically to use 3 and 7 as well. So if they didn't specifically tell us to use 3 and 7, we could have used other things. It's generally good practice to use, when you do an approximation, to use the points that are closest to what you're trying to approximate. So, not too bad. Use a left Riemann sum with 3 subintervals indicated by the data in the table to approximate the value of 0 to 12. Interpret the meaning of 1/12 of that. Okay, so I have a graph already, so I'm just going to use the graph. And we want to do a left Riemann sum. So it means we're going to use the left side of where the graph touches. So it starts at 0. This is t equals 0. This and that. And so this is going to be an overestimation because we have some of the box that's outside the graph. And that's due to it being a decreasing function. So this distance right here, this height, is going to be 100. This width is going to be 3. This height right here is going to be 85. Because we're looking at right there. This is going to be 4, 7 minus 3. This will be 5, and that height will be 69. So when we find the area of all these boxes, this is going to be 100 times 3. I should probably do it down here. 100 times 3 plus 85 times 4 plus 69 times 5. And they want 3 subintervals, which is good because that's what I used. So 100 times 3, probably 300, plus 85 times 4, plus 69 times 5. And you can do this on your calculator. I'm again using Wolfram convenience, and I get a value of 985. And that's going to be degrees Celsius times minutes, because it's the area under there. So then we want to interpret the meaning of 1/12, 0 to 12 C of t dt. So this is the average temperature over the period of 0 less than t less than 12. So if I go back up to my graph, all reliable. Actually, I should probably figure out what that is real quick. So we take basically the integral we just did, which gives us 985. We divide it by 12, which is the same as multiplying by 1/12. And that gives us a value of 82 degrees Celsius. And what that means is the average, if we took all the area under these curves, these boxes, these Riemann sums, and squished them into a rectangle, it could be a rectangle that was 85 high and 12 long. And so basically it's like take the area and rearrange it so it's flat. That would give us the average temperature. Let's see if there's anything else they wanted there. Interpret the beating in context of this problem, average temperature. So for 12 to 20, all right, so moving on, the rate of change in temperature is modeled by that. So they give us the derivative, not the value. Where C prime of t is measured in degrees Celsius per minute, find temperature coefficient at time t equals 20, show this application. Okay, so what we're going to do is, so we have dc dt equals negative 24.55 e to the 0.01 t. So what we're going to do is we're going to over t. I know handwriting is terrible. I apologize. So what we're going to do is we're going to take the integral of both sides. So c is a function of t, and this is only going to be between 12 and 20, is negative integral 24.55 e to the 0.01 t all over t. This will be from 12 to 20. Yes, and I don't know how to do this. Yeah, it's going to be a huge pain. If that t was on top, I would be like, oh, integration by parts. But I don't. So I'm going to just put this in my calculator. There we go. And due to the magic of video editing, I put it in there because you don't need to see me put that in there. Boring. So I'll do window. Let's do 12 to 20. Do I want to do that? Maybe. Yeah, we'll see. And then I'll do negative 5 to 5. That works. And then we will graph this. Okay, seems reasonable enough, I suppose. Second, calculate. We're going to do the integral. This is the part where it's like, you can use your calculator. I wish there was, is there a better way of doing this? I don't know. So it's telling us where to start. So this is why I probably should have said it was 0 to 20, because that means I have to go across the entire graph to make this work. This is probably making it the most accurate, but also the most tedious. Exceedingly tedious. So once this gets over, I should probably edit this out. I'm not going to, but I should. So we go 12 to bump, 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 20. There we go. Click. It does the calculation thing. It should give us a negative number because it's below the, there we go, negative 14.67 equals negative 14.67. So this is going to be the yes. So it's going to be that plus a constant. And that constant is going to be where we started at. So this was the temperature from 12 to 20. So we have here then represents the change in temperature from 12 to 20. And we know at 12 we were at 55 degrees. So what we're going to do then is we're going to add the change. We're adding a negative, so it's going to be the same as subtracting. 55 minus 14.67. So we have 55 minus 14.67, and I get a value of about 40.33 degrees Celsius. And that'll be the temperature at T equals 20 minutes. So this is what we started at. That's our initial condition. We look at the change, add them together, and that gives us our final result. Make sure we got it. Interpret the meaning and the context of the problem. Nope. Show the setup for your calculations. That's the setup for our calculations. And the reason they say kind of show your setup is that way we just put it in the calculator. For the model defined by this, can it be shown that this value right here can be shown that at that blah blah blah, determine whether the temperature of the coffee is changing at a decreasing rate or an increasing rate, give the reason for your answer. Okay? So let's take a look at this. I'm going to crop this a little bit. So we have, for part D, for the model, can it be shown that remember the temperature of the coffee is changing, so C prime of T, at a increasing or decreasing rate. So we want to find the derivative of C prime of T, which is going to be C double prime of T. So this is asking us to determine whether the second derivative is positive or negative, decreasing rate or increasing rate. So what we're going to do is we're going to take this 0.2455 e to the 0.01 t 100 minus t all over t squared. So we know that this is positive because squared. This we know is positive because 0.2455 is positive, and e to an exponent is also always going to be positive, and this will be positive for 12 less than t less than 20. So basically it's going to be between 80 and 88. So since all the terms are positive, that implies that C prime prime of t is positive, therefore increasing rate. So we know that this is going to be at an increasing rate over this interval. All right, so let's see, that answer the question mostly? All right, yep, and that's all we had for that one. So not too bad, not too bad. Yeah, it took a little over 15 minutes. We're probably good. All right, so now let's look at number 2. Number 2. Up. So for number 2, we have a particle which is moving along a curve in the xy plane, has position x of t, y of t at t time t seconds, x of t, y of t, measured in centimeters. All right, I'm going to make sure I know the centimeters part because I'm used to meters. And it's measured in seconds, which is standard. It is known that blah, 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 at time this. Find the speed of the particle at t equals 2 seconds. Show the setup for it. So they want us to show the setup because they, I think they're going to allow us to use our calculator. X, Y, and I guess I could probably have like a third plane here to show the t, but I'm not going to. So we want t equals 2. This will be t equals 2. Do this a little bit differently. This will be t equals 3. No. T equals 2. T equals 2. And this is at 3, 6. And this will be at t equals 0. Yeah, maybe. So we want to find the speed of the particle at that time. So the speed of the particle is going to be the x value squared plus the y value squared square rooted. To view this, we're going to look at this as just adding. So speed is a vector. When you add vectors, you add them vectorially, meaning triangles, Pythagorean theorem. Pythagorean? I don't know. Not important. Dead language. Doesn't matter. 8t minus t squared, negative t plus square root of t to the 1.2 plus 20. And this is going to give us the, and then we're just going to square those. So we're going to do, and we can just put this straight in the calculator. We're going to get speed equals square root of 8t minus t squared plus negative t plus t to the 1.2 plus 20 square rooted squared. And we're going to plug in t equals 2. Yep, not too hard. You can do this in your calculator. I'm going to do this on Wolfram because I can. So we'll do square root of quantity 8t minus t squared plus quantity negative t plus square root of t to the 1.2 plus 20 quantity squared. Oh, and where t equals 2. There we go. And we get a result of the speed, which is this value right here, equals 12.3 at t equals 2 seconds. And I should put units on this, so this is centimeters per second. cm for centimeters. Alright, got that, not too bad. Find the total distance traveled by the particle over the time period from 0 to 2. Alright, so this is a little bit challenging. Maybe not. So we're going to think of the arc length formula. So we have some sort of graph, and we start here, and we're told it has an x speed and a y speed. This will be delta y, this will be delta x. This is the x-axis, this is the y-axis. And the idea here is you're going to use this to build up a curve from t equals 0 to t equals 2. So the way I'm going to do this is, since we have delta x, delta y, we're going to add them as vectors, because they are vectors. And I'm going to write this as delta x, I'll call it delta x, delta t squared, plus delta y, delta t, also squared, square rooted, because Pythagorean theorem, x squared plus y squared, square rooted, dt. And we're going to go from 0 to 2. And so what's going to end up happening here is we're going to have integral from 0 to 2. And this should be similar to the arc formula, which you're used to seeing. Is probably 1 plus, you're used to probably saying dx squared plus dy squared square rooted. Well, what happens is you factor out like a dx squared there, and you get dx squared times 1 plus dy dx, that's supposed to be a y, squared. And when you simplify that, you get 1 plus f prime of x, where f prime is the same as dy dx. And you have dx integral. So this is probably the arc length formula that you're used to seeing. This right here, exact same concept. We just we don't have to simplify it because we're given dx dt, we're given dy dt, and we can just look at it straight away like that. So from this point, we're going to copy, paste, do some cropping, and we're going to have 8t minus t squared plus negative t plus t to the 1.2 plus 20 squared dt square rooted. And this is very similar to what we just did, except now we're going to integrate it. So I'm basically going to use Wolfram again. Integral of for 0 less than t less than 2. And I'll show it to you what I'm doing right here so you can get kind of a warm fuzzy. It's supposed to be 8t? I don't know. Blah 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 blah. Did I forget a 1.2? No, I put the 1.2 there. They just simplified it. Maybe 15.9. That seems as reasonable as anything, I suppose. So this equals 15.9, and it'll be in centimeters. So you could do the same thing on your calculator. You basically just put it into your calculator like you did for y, you graph it, you do the integral, same thing, 0 to 2. Let's see what they ask. Find the total distance traveled. Yep, distance traveled, so how far it changed positions. So if they found its total position, that would be different, because then we'd have to use like the, if they found like the position at 0, then we'd have to use like the final point. So the setup for your calculations, yep, and that's kind of a hint that, oh, you can use your calculator. I'm like, yes, we can, that's good. So now we want to find the y-coordinate of the position of the particle at time t equals 0. Show the setup for cal. Okay, same idea. So I'm going to draw, we have our graph up here. We know that its final position at t equals 2 is 3, 6. And we're concerned specifically with the y-coordinate. So we know it's at 6. We know it traveled a distance of 15.9. So it traveled 15.9. So what I'm going to say here is I will put forward that y initial plus 15 point, actually we don't want to use 15.9, we want to use just the y coordinate. So 0 to 2 of negative t plus t to the 1.2 plus 20 square rooted dt. So we're integrating with just respect to y. Putting that into a calculator, we're going to do integral of negative t plus square root of quantity t to the 1.2 plus 20 dt for 0 less than t less than 2. So what I did here is I did just the y portion. Integral negative t blah 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 blah, and it gives us an answer of 7.17, which might be true. I'd expect an answer less than the total distance traveled. Probably, yes. 7.17. So I'm going to say that y initial plus change in y equals y final. Therefore, y initial is going to be y final minus change in y, which is going to be equal to 6 minus 7.17. And so I'm going to do 6 minus 7.17, and that gives me an answer of y initial is negative 1.17. So y equals, so then I'd probably say something formally like y equals 0, or y equals negative 1.17 at t equals 0. Yep, not too bad for the y coordinate. And then we showed our setup because we use the calculator to do the integral for us. Again, we go here, put in y, and the calculator, do the integral. Huge pain, totally possible, just a pain, tedious. So now we want to find for t is less than or equal to 2 is less than or equal to 2, t less than or equal to 8, the particle remains in the first quadrant. Find all the times in there where the particle is moving towards the x-axis. Okay. So for D, I'm going to do this one over here just because I can. So we have our axis. This is the first quadrant, quadrant 1, first quadrant. We want to find where the particle is moving this direction. So we want to find when y prime of t, which we know is equal to negative t plus square root of t to 1.2 plus 20 is less than 0. Okay, and the way we're going to do that, we're just going to graph it in the calculator. Again, plug in your y. I'm not going to do that because I have Wolfram, which is wonderful, and I'm not going to feel myself restricted to what I would actually be using if I was taking the test. So square root of 1.2 plus 20, and I'll say less than 0. So what that looks like then, okay, so it's going to look something kind of like this. So we know that negative t blah 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 less than 0 means moving towards the, it's moving downward. It's just when the first quadrant that's towards the x-axis. So that means that t is going to be within this region right here. Okay, sounds good. And so for that, we can say that therefore t, I'll do this a little bit differently. 5.22 less than t, less than or equal to, and then we probably want a real value, 8. So it's going to be less than or equal to 8. And before this interval, the particle is moving towards the x-axis. Yep, and then give a reason for your answer. It's kind of difficult to be like, hey, what's your entire reasoning here? I'm just going to say this. I'll call this picture up here with the particle moving towards the x-axis as my reasoning. Towards implies y prime of t less than 0. Pow, and then calculations. So that's how to approach the first two problems. Hope that helped a little bit. And then I'll go through the other problems probably a little bit later. So first problem, not too bad. Again, the hardest part for this is always the fact that you don't have enough time to think through things properly. So really it's the idea that you're kind of just running through these and doing the best you can, get as many points. You don't have to be perfect because the highest score is like a 5, and I don't know, probably like 50-60%. So you want to be good, not perfect. All right, and we'll do the non-calculated portion later. Take care. See you next time. Calculus BC, Section 2, Part B. 4 questions, 1 hour, 50 minutes per question, 20, 24. All right, see what we got going on here. So we have question, is it number 3? Number 3, because we already did the calculator portion. This is the no calculator portion. I'll probably still use calculator though, just because I'm lazy. I know, it's a crutch. I don't care, I'll get over it. The depth of seawater at a location is modeled by the function h that satisfies the differential equation that, where h is measured in feet and t is measured in hours after noon. Okay, so that's kind of a weird metric. It is known that h of 0 equals 4. Okay, and they give us a little dot there. Portion of the slope field for the differential equation is right. Sketch the solution. Y equals h of t to the point 0. Okay, this is just follow the lines. Whoop, 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 whoop. There we go. That's the solution right there. Because the slope field basically gives you the slope at every point, and so it's the idea of Euler's method. I think Euler's method. Basically, we just do each little point. So then, let's see. We have 0 less than t less than 5. It can be shown that h of t is greater than 1. What are we even looking for? Depth of seawater. So the depth of seawater is always greater than 1. Okay. Oh, that just keeps this top part positive. That's all they're going for. Find the value of t for 0 between t between 0 and 5, at which h has a critical point. Determine whether the critical point corresponds to a relative minimum, maximum, or neither. Blah, blah, blah. Justify your response. Okay. So, let's see here. I'm going to do it this way. I think they're called arrow charts. I don't know. It's going to look like this. So, we're going to start by looking at some points. And the first point I'm going to look at here is going to be, let's see, one between 0 and 5. So I'm just going to put 0 and 5 up here, because that's kind of like our bookend, so to speak. And let's start by looking at when this equals 0. So we have 1/2 h minus 1 cosine of 1/2. So cosine of t over 2, not 1/2. Yes. And so we want to find out when this equals 0. This equals 0, so cosine of t over 2. So we want to find out when this portion here is equal to 0, because that'll make the whole function 0. So we want to find out when cosine of t over 2 equals 0, and cosine, we look at our 0, pi over 2, pi, 3 pi over 2. That's going to equal 0 at pi over 2 or 3 pi over 2. And then it keeps going as well, so it'll be 5 pi over 2, etc. So I'm going to, what is 5 pi over 2? 5 times pi over 2, that's 7. So we're not going to worry about that. Let's look at 3 pi over 2, that's 4.7. So we're going to have two critical points. We're going to have pi over 2, which, and I'm going to do 3 pi over 2. So 3 pi over 2 is about 4.7, and a normal pi over 2 is going to be 1.5. I probably could have guessed that one. And so the idea here is we're going to get cosine of t over 2. I think I went a little bit too quick on that. So this implies that t is going to equal 1, or t is going to equal 3. Because if we plug in t equals pi, t equals pi, or t equals 3 pi, that's going to give it 3 pi is going to be 9, 1 pi is going to be 3.14. So we're just going to have a single pi. They're trying to make this problem easier, and I'm making it harder. So we'll go with their method of making it easier. So to backtrack what we did real quick, we wanted to find out when this equaled 0. That's going to equal 0 when the cosine of t over 2 equals 0. Cosine will equal 0 at pi over 2, 3 pi over 2, 5 pi over 2, and it keeps going. So it's already of the form pi over 2, that's what we want, and it gives us of the form t over 2. So it's like, oh, well, t then equals pi. The other option would be t is 3 pi, and 3 pi is greater than 5, so we just don't worry about it. Alright, so then find the critical point. So this is going to equal 0. And so what I'm going to do then is I'm going to plug in 0 and 5. So if we have 1/2 h minus 1, we know that's positive because they tell us. Cosine of, I'm going to do 5 over 2 here equals, so cosine of, actually I'll start with 0. 0 over 2. That's cosine of 0, that's positive. So this is going to be positive. So this whole thing right here is going to be positive. So what I'm going to do then is I know on the 0 side here, this is going to be positive. 1/2 of h minus 1 cosine of 5 over 2. So let's do, 5 over 2. So 5 over 2 on this graph is going to be right out here. That's going to give us a negative. So this is going to be negative. So this is going to be negative. So what we're seeing here, looking at our arrow chart, on this side, the graph is going up. On this side, graph is going down. So it's going to be a maximum. So we'd say something like, by the first derivative test, So this is the first derivative test. If we looked at the second derivative and we found the concavity, that would be the second derivative test. When we're looking at this, when we're basically drawing this hill using the first derivative, that's the first derivative test. This is the formal way. You're not supposed to say like, oh, look at the arrow chart. See, mountain, maximum. Though true, the more formal way of saying that is first derivative test. So you say first derivative test, and we say maximum at t equals pi. There we go. Adequate. And you should be a little bit clearer than this. I know I'm moving quick. You're going to be moving quick. Perfection is not the goal here. Justify your answer, blah, blah, blah. Determine whether critical point, find the value at which h has a critical point. Determine whether the critical point corresponds with a relative minimum or maximum, or neither, blah, blah, blah. Justify your answer. Okay, use separation of variables. So they don't actually want us to find the actual maximum depth, I don't think. Use separation of variables to find h of y equals h of t, the particular solution to the differential equation. Okay, so no idea what's going on, but we're just going to rewrite this and kind of work through it. They said separation of variables, so I'm like, all right, I'll do separation of variables. Hopefully this is easy because I am not that clever. So I'm going to say 1 over h minus 1 equals, actually I'll do this a little bit differently. 2 over h minus 1 dh equals cosine of 2 over t dt. So we separate the variables. Now we just need to integrate both sides, which will probably be the tough part here. I'm going to do some use substitution. I'm going to say that h, small h, equals h minus 1. Therefore, dh equals big DH. I'm going to say that big T equals t over 2. Therefore, dt equals dt over 2. And I'm just going to, this is terrible notation, but it's going to happen. So then we can say that 2 over little h dh equals cosine of big T dt. 2 integral, cancel the 2's. Integral of 1 over h is going to be natural log of h. And that integral of cosine is positive sine. So we're going to have sine of t dt, or sine of t plus c. We're going to go back to our original variables. So this is going to be natural log of h minus 1 equals sine of t over 2 plus c. To get rid of the natural log, I'm going to take e to both sides. So it's going to be h minus 1. I assume we're solving for e to the sine of 2t of t over 2 plus c. Now let's take a look up here, see what's going on. Use blah 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 to find y of t. They give us a particular solution, so we need to solve this. For c, particular solution means just solve for the variable c, the constant c that we have. So to do this, I'm going to rewrite this as e to the sine of t over 2, e to the c, which I am then going to relabel as c1. It's just a different variable, different constant. So we're going to have h equals c1 e to the sine of t over 2 plus 1. And we know that when t equals 0, h equals 4. So when t equals 0, h equals 4. So we have 4 equals c1 e. Sine of 0 is 0 plus 1. So c1 e to the 0 is 1. c1 equals 3. So then h of t equals 3e sine of t over 2 plus 1. And that will be our particular solution for this function using separation of variables. All right, adequate? Maybe adequate. A lot of work there. Whoop, didn't mean to go that far. Maybe. Close. All right, so that's how I would do part number 3. Let's take a look at number 4. Oh, that took me about 15 minutes, so it's probably about the right pace that I'm going. Though it's one of those things where it is easy to get on the wrong track with these. If you don't like exactly hit the correct concept the first time, like you can easily waste a lot of time. We have a graph of a differential function f shown above from -6 to 7. Has a horizontal tangent at x equals 2, meaning the slope is 0. It's a maximum. And is linear from 0 to 7. Let R be the region in the second quadrant, bounded by the graph of f, the vertical line x equals -6, and x-axis is blah blah blah. Region of area R is 12. Okay, the function is defined by this. Find the values of g of -6, g of 4, and g of 6. Oh, okay. So basically what this is saying is when we plug in, so for A, so we have g of 4, I'll do g of -6 first. G of -6 equals 0 to -6 f of t dt, which is going to be the region -r, because it's going from 0 to -6, which is -r, which is going to be -12. G of 4 is going to be 0 to 4 f of t dt. That's going to be this triangle right here, which is a 4 by 2. I'm going to call this region A, call this region B. So A, so I'm just going to do this little crazy notation. I'm going to call this region A, which is 4 times 2, which is 8, divided by 2, which is 4. So it'll be 4 units. And they don't give us any specific. Nope. So we don't have to worry too much about the units, like units squared or something like that. So g of 6, that's going to be the same concept. 0 to 6, f of t dt. And I don't know if you have to write all this. I'm being a little bit more formal than I normally am. A minus B, region A minus region B. That's a 1 by 2. So this is going to be 4 minus 2 times 1 is 2, divided by 2 is 1, which will give us 3. Yep, And so it's a easy problem that is just asked in a difficult way, which is par for course. The function g, defined in part A, okay, find all values of x on the interval 0 in which the graph of g has a critical point. The function g, find all the values of x from 0 to 6 in which the graph has a critical point. Okay? So I am not going to overthink this. So g of x equals integral x f of t dt. And this is, let me look this up just so I don't mess it up. This is going to be the fundamental theorem of calculus. Fundamental theorem of calculus. I know, we can't look this up on the AP exam, so I'm not going to even pretend that this is what you would be going through. Yes. Is that a good way of saying that? Yes. Let me grab a little screenshot here. Boom. And this is just straight off of Wikipedia. Boop. Copy. Paste. So the idea here is this g of x is going to be the integral of f of x. And we kind of saw that before, basically we're taking the integral. So if we take the derivative of both sides, if this is, we'll call this f of x, and we'll say that g of x equals integral f of x. So then we want to find g prime of x, which is going to be just f of x. So what I'm saying is this g of x, that's the integral of this function shown up here, when I call this function f of x. So if we want to find a critical point, we want to find where the derivative equals 0. So we're going to find, so let's say something like, for critical points, I know handwriting is terrible, your handwriting will also be terrible because you are writing quickly. For critical points, the derivative equals 0. So the derivative, g prime of x, is going to equal f of x, and f of x equals 0 at x equals 4. So right here, that is going to be our critical point for g of x, because g of x is the integral. We take the derivative of g of x is going to give us f of x, and so then we find out where f of x equals 0. They ask a simple question in a confusing way. That's just, and this is one of the reasons why I know the fundamental theorem of calculus is important. I just find it less enjoyable. So, but that's what they're going for on this one, I believe. Give a reason for your answer, and then the reason would kind of just be this portion right here. For critical points, derivative equals 0, g prime of x equals that, and you might want to say the word fundamental theorem of calculus, because that's kind of what they're going for here. The function h is defined as this. Okay. Find the values of this. Huh, okay. So this is, again, fundamental theorem of calculus. And they use f, they use f prime of t. I think that is actually f of t, so we can probably actually go with that. Yep, graph of f. The function h is defined as that. Okay, find the values of this. So let me go back to the fundamental theorem of calculus. So the part that we're going to use for this, yes. Oop. Again, use a little screenshot here. It's a corollary. So if we go from a to b, that's going to be the integral of f at b minus integral of f at a. So what this is saying is that h of x would equal the, so this is the derivative, that's the integral, so this is just going to be f of x minus f of negative 6. So this says take the integral of the derivative is just the normal function. So f of x, yes. So yes, true. So h of x, which would be h of 6, would be f of x minus f of negative 6. Is that true? Does that seem... Oh, and they want us to plug in the value of 6. So this would be f of 6 minus f of negative 6. Okay, I think we can do that. So then this would be f of 6, which is negative 1, minus f of negative 6, which is 0.5. So this is going to give us negative 1 minus 0.5. So it'd be negative 3/2. Yeah, I'll go with that. So then we want to find h prime of x. So h prime of x is going to be, so if we have the integral from negative 6 to x, we take the derivative of that. Let me check real quick, make sure. Get this reasonably correct. So for this, we're going to use this idea. Whoop. Copy. And again, just straight from Wikipedia. We have, so when we want to take h prime of x, what we're going to do is we're basically going to plug in x. So this is h of x equals negative 6 integral x f prime of t. Yep. F prime of t dt. Therefore, h prime of x is going to be f prime, and we're just going to take this x and plug it in there. One other nuance to do it, and this is kind of just memorizing the way it's going to pretty much always work, is you plug in x, but then you also multiply by, because of the chain rule, the derivative of x. So this is actually f prime of x times the derivative of just x, which is 1, which is why we kind of are going to ignore it in this case. So h prime of 6 is going to be f prime of 6. And so that's going to give us h prime of 6. So at 6, this slope right here, it's rise over run, so it's going to be negative 1 and 2. So it'll be negative 1/2. That's just the slope at x equals 6. And since that slope is constant, we're then just going to use this same concept to find the second derivative. F double prime of 6 equals 0 because linear slope. Whenever you have a linear slope, the second derivative is going to be 0. And so that's how we're going to do the second part there. Blah, blah, blah. Show the work that leaves your answers. Yep, so the work then would be this portion for the first part. Then when we take the derivative, we found h prime of x by just basically plugging in x. And then took the derivative of the derivative, which gives us 0, which is the second derivative. So that's how we approach that one. Fundamental theorem of calculus. It's important, but for most of those, I just memorize how to do the answers. All right, so that's how I do part 2, or question, was it question 4? Question 4. All right, let's take a look at question 5. Boop, see how we're doing on time. Yeah, we're about on pace. All right, question number 5. The function f is twice differentiable for all x with f of 0 equals 0. So they're giving us the derivative, but not the function. So I'm going to rewrite this table just because I want to. It's just how I feel a little bit more comfortable. So it'll be 0, pi, 2 pi, 5, 6, and 0. And what I did is I just put f of x in the middle and f double prime of x on the bottom. I probably won't use f double prime of x, but I figured I'd put it there just in case. They also give us the info that f of 0 equals 0, so we can plug that point in. Blah, blah, blah. Okay. For x greater than or equal to 0, the function is defined by this. Okay? So that looks kind of like a arc length formula. And fundamental theorem of calculus. Okay, find the value of h prime of pi. Show your work that leads to your answer. So we have h of pi equals 0 to pi of 1 plus f prime of pi squared, square rooted. dt. That is not useful, is it? I don't think it is. Use fundamental theorem of calculus. Click. Clack. Make it a little bit smaller. This right here. So f of x equals this. That's kind of the format we have. The derivative of the left side equals, basically just plug in the x. And we also have to multiply by the derivative of x, but since we're just going straight to x, it just is 1. So integral, so I'm going to say that h prime of x equals 1 plus f prime of x squared, square rooted. Yes. Therefore, h prime of pi is going to be 1 plus f prime of pi. So f prime of pi is going to be 6. So it's going to be 36. I'll write it as 6 squared. Square rooted, which can be equal to square root of 37. Okay, so that will be the value of h prime of pi for that. So take a step back real quick. This is set up fundamental theorem of calculus. They want us to find the derivative of h. The way we do that is we plug x in for t. One thing we'd do if this is not just a simple x, we'd also have to multiply by the derivative of what it is. So if it's like x squared, we plug in x squared, but then we'd also have to multiply it by 2x, the derivative of x squared. What information does this provide about the graph of f? So oh, they're talking about arc length. And that's why I was like, oh, it looked like an arc length. That's what they're talking about. So what information, I'm going to do B right here, does this provide about the graph of f? So h of x is the arc length of f from 0 less than x less than pi. So this is the arc length formula. You just have to look at them and recognize, like, oh, arc length formula. Use Euler's method starting at x equals 0 with 2 steps of equal size to approximate f prime of 2. Show the computations that lead to your answer. Okay, so I'm just going to copy and paste this down here. When I do Euler's method, I try to be as formulaic and methodical about it as possible. So I'm going to try to start over and do it from here. So use Euler's method starting at x equals 0 with 2 steps, approximate size, find 2 pi. So we're going to start with x equals 0. I'm going to start by drawing a picture. So we start at 0. We're told that 0, 0, and then we have a positive slope. So this and that. So our first step is going to be like this, and that's going to be at pi. Our second step is going to be like that, and that's going to be at 2 pi. I'm going to call this x. I'm going to call this y, just for convenience. I could do f of x, but it's one of those things where it's just easier to write this way. So x is that, y is that. Delta x, our change in x, we're going to take 2 steps. So first step is going to go to pi, because our second step will go to 2 pi. Our change in y, then we'll do dy dx. So our change, our slope along this region is going to be 5, because our slope right here, slope at 0, is going to be 5. So we know our slope at this point at x equals 0 is 5. So then our change in y is going to be our change in x times dy dx. You could think of it as multiplying together. The delta x is canceling. It's just going to be these two things multiplied together, so we get 5 pi. All right, so our x step was pi, so that's going to be right here. Our y change is 5 pi, so it's going to be right there. Our change in x is again going to be pi. Dy dx at x equals pi is 6, so it's going to be 6. So delta y is going to be delta x times delta y over delta x, which is pi times 6, which is 6 pi. Therefore, our final x position will be 2 pi, which is where we want to be. Our final y is going to be our y plus our change in y, which is 5 pi plus 6 pi, which is 11 pi. And this is the answer we're looking for, so we're not going to go any further. We could, we're not going to. Using Euler's method, blah, 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 show the computations that lead to your answer. So, see table. F of 2 pi is approximately 2 pi, comma, 11 pi. So, they don't care about the x value because the x values are already listed there. So, f of 2 pi is approximately 11 pi. And this is just a table to calculate f of 2 pi using Euler's method. So I'm not sure how the grading is on how tolerant they are of, like, oh yeah, the table, it's obvious. I would go for it. We'll see what happens. I know, it's easy for me to be all cavalier with your AP exam scores, but yeah, there's only so much you can, so formal you can be with these because you just don't have time. Find integral of t plus 5 cosine of t over 4. Show the work that leads to your answer. All right, so this is almost like a completely different question. It might be that this might actually be like what they used for to create the table. I don't know. I don't really care. As far as we're concerned, we're just finding an antiderivative here, an integral, if you will. So this looks like integration by parts. So that's how I'm going to at least approach it. So I can never remember the formula for integration by parts, but I do know that it is just the inverse of the product rule. So I write out the product rule, rearrange things a bit, and then so the integral of u dv equals uv, because the integral of uv quantity derivative is just uv, minus integral v du. And then to choose the u, there's a mnemonic, either Liadi or I late, pretty much the same, and whichever one is highest, going from top to bottom, is usually what you want to choose. Another way of thinking of it is the thing that's going to go away, you want to set equal to u. So in this case, we have an algebraic, which is t plus 5, and we have a trig, which is cosine of t over 4. So since the algebraic is higher, that will be our u. So u is going to be t plus 5. dv is going to be cosine of t over 4. V is going to be integral of cosine is positive sine, so it'll be sine of t over 4. But when we take the derivative, so we're going to have to multiply that by 4. And we could figure that out more formally using u substitution. So we'd say u equals t over 4, and then kind of work our way through it. I'm kind of haphazardly guessing checking, which sometimes it works great, sometimes it's a terrible, terrible disaster. So when you take the derivative of sine, we get cosine t over 4, and we pull out the 1 over 4. 4 over 4 is 1, therefore, yeah, okay. That'd basically be saying that this is the same as 4 over 4 like that, which is 1. All right, so maybe adequate. And then do the easier one, du equals dt. I should probably have a little dt over here as well. All right, so that looks plausible, if not even correct. So now we're going to say that the integral of t plus 5 cosine of t over 4 dt equals u times v, so t plus 5 times 4 sine of t over 4 minus integral of v du, so it'd be 4 sine of t over 4 times dt. This part here will stay the same. I know, you can't really do the copy and paste thing on the AP exam. It's alright. So, the integral of sine is negative cosine? I think so. So this is going to be negative 4. I'm actually going to do kind of a sidebar here. So I'm going to say that big T, I'll use big T equals t over 4, dt equals dt over 4, for big dt equals dt. All right. So then that becomes cosine. So this is integral for integral sine of, do this again, for integral sine big T, and then dt is going to be dt, that becomes 4 times 4, which is 16, and that becomes 16 cosine negative of big T, which is the same as t over 4. Okay, so this is, we have negative 16, but it's negative, so it's going to be plus 16 cosine t over 4 plus c. We have to add that plus c because it's an indefinite integral. So that's how I'd approach this problem. The key idea here is recognizing integration by parts, or integration par partie, as the French say, and choosing your u, memorizing the formula, maybe memorizing the mnemonic, and then just working your way through. So not a particularly easy problem, but it's possible. All right, see what we got? Yeah, maybe a little bit slow. So now we have problem number 6. Maclaurin series for a function at f is given by this and converges for f of x for all x on the interval. So it converges. Interval of convergence. It always converges on the interval of convergence. They probably don't need that extra. Yeah. It can be shown that the Maclaurin series for f has a radius of convergence of 6. Okay? I believe. Determine whether the Maclaurin series for f converges or diverges at x equals 6. Give a reason for the answer. Okay. So they tell us, so just because it has a radius of convergence doesn't actually mean it converges or not at the endpoints. So that's something we're going to have to figure out. So to do that, I'm just going to plug in 6 and see what happens. So n equals 1 to infinity of n plus 1, 6 to the n, all over n squared, 6 to the n. So what I did was I plugged in x for 6. So plug in x equals 6. Cancel, cancel. I'm going to rewrite this as n times 1 plus 1 over n. This is n squared cancel, cancel equals 1 plus 1 over n to the n. I'm going to say limit comparison test. And we could actually probably do the direct comparison test. I'm just going to say that, and ideally the grader is like, oh yeah, I know what they mean. So this is basically going to be the same as 1 over n, which is harmonic series. And you might have heard like the p-test, where basically if the power right here is greater than 1, then it converges. If it's equal to or less than 1, then it will diverge. Harmonic series, therefore, diverges at x equals 6. So for x equals 6, diverges. So negative, if it's for negative 6 though, it will converge because then you get an alternating series. When it's positive, x equals 6, you do not have that. So it can be shown that blah blah blah, f of negative 3, and the first 3 terms equals that, show that this is less than 50. Alright, so I'm going to draw a quick picture of what I think they're saying here. So this is an alternating series because we've got the negative 3. And I'm going to draw a picture of the graph. And I'm going to draw a picture of the graph on the other side, the negative of it. And basically what we're going to have is this will be, you start at probably what, 1? This will be 1. This will be 2. This will be 3. This will be 4. So the idea is each time, this will be, I'll call this A1, A2, A3, A4, A5, and then S3 is going to be the sum of the first 3 boxes. So S3 is going to be equal to A1, I'll put little A's here just because it makes me feel better. A1 plus A2 plus A3. So S infinity would equal so for the first three terms, show that first three terms of the series, so that F3 minus S3. So S infinity, which is the same as F of 3, minus S3 is going to be equal to A4 plus A5 plus A6 plus dot dot dot. Since this is an alternating series, and that's how this A4 will be bigger than that the first three terms. It can be shown that terms series equals this. Show that. So this, each time it gets closer and closer. So A4 is going to be bigger than because each term is closer to the actual value, to the let's see, actual, this is, I am not saying this well, actual value of, because each term is there's three terms. I'm not even going to try and explain that. I'm just going to leave it like that. And hope I'm going to write that up here, which is because each term gets smaller, each box in this gets smaller. So I'm going to say that this is then going to be less than A4. Yes, I don't have a good way of explaining it. Basically, each box gets smaller. I should probably think of a better way of explaining it. Alright, and if I ever teach this, I probably will, but I have not yet. So basically, our goal here is to find, what they're saying here is find A4. So A4, I'm going to copy and paste this, just so I have something to look at. We want to find the fourth term. So, summation. So when n equals 4, we have 4 plus 1 all over 4 squared minus 1/2 to the 4th. So this is going to be 5 over 16 minus 2 to the 4th. 2 to the 4th is 16. So it's going to be 1 over 16. 16 times 16, that's 256. So this is negative 5 over 256. And all they care about here is the absolute value. Oh no, that's positive. I took the negative out. I should not have, because it's negative to the 4th. It will be a positive value. So it's 5 over 256, which is less than 5 over 250, which is the same as 1 over 50. So this 1 over 50, basically what that means is that it is less than 5 over 256 is what happens when you plug in 4 for n. So roundabout way, I would say then, and then with confidence, I would say that the absolute value of f minus 3 minus s3 is less than 1 over 50. And this is the work to show it. Kind of my reasoning and justification behind it. Not as strong as I would like, but that's what I got. So that's where I'm going to go with. All right, so that's how I would approach part B. Part C. Find the general term of the Maclaurin series for f prime, the derivative of f. Find the radius of convergence of this. Okay, so they want us to find the general term of f prime, the derivative of f. I think that's easy. So we have f of x equals summation n equals 1 to infinity of n plus 1 over n squared times 6 to the n x to the n. Therefore, f prime of x is just going to be the derivative of this. N plus 1 over n squared times 6 to the n. Then we do n times x to the n minus 1. Find the general term of f prime of x. Check. Then find the radius of convergence. Okay, then they want us to find the radius of convergence of this. There might be an easy way to do this. Oh, I could probably cancel out one of the n's real quick. But I'm not quite sure the best way to do it. So I'm going to default to the ratio test. I know, super messy, and I apologize. So ratio test. So I'm just going to write down ratio test. And the idea behind the ratio test is you take the next term divided by the current term, and take that limit to infinity, and if that gives you less than 1, then converge. So an plus 1 is going to be n plus 2 x to the n all over n plus 1 6n plus 1. 1 over an is going to be n times 6 to the n all over n plus 1 x to the n minus 1. I just flipped it up. And so then an plus 1 all over an is just these multiplied together. So we have n plus 2 x to the n all over n plus 1 6 to the n plus 1 times n 6 to the n all over n plus 1 x to the n minus 1. Do some simplifying here. So this becomes n times 1 plus 2 over n x to the n minus 1 times x times n times 6 to the n all over n times 1 plus 1 over n 6 to the n times 6, and we'll do n times 1 plus 1 over n, I'm just factoring out the n, times x to the n minus 1. Alright, super messy, hopefully things will get cleaned up. So x to n minus 1's cancel, 6 to the n's cancel, these n's cancel, that n cancels, that's going to go to 0, that's going to go to 0, that's going to go to 0, and we're left with x over 6. Which means that x has to be less than 6. So this has to be less than 1, which means that x is less than 6. So radius of convergence is equal to 6. So the radius of convergence stayed the same. So I know I went through that super fast. If you're going to use the ratio test for this, ratio test takes a while. You're going to have to go kind of quick. Alright, so that's how we do, and I'm just going quick because I know it's running low on time, which means we probably have to go quicker. Find the radius of convergence of the Maclaurin series f prime. Let g of x equal this. Use the ratio test to determine the radius of convergence of the Maclaurin series of this. So we're going to use the ratio test. So an plus 1 is going to be, normally I'd write out the ratio test, be like, hey, this is what I'm plugging in. You don't have that much time. So we do n plus 2, x to the 2, n plus 1. So I'm going to do this as just 2n plus 2. I know I'm taking shortcuts. Probably should not. N plus 1 squared. I know I'm taking more shortcuts. N squared plus 2n plus 1. That's just n plus 1 quantity squared. 3 to the n plus 1. So ideally, I'd be a little bit more formal, take a little bit more time. Not happening. 1 over n is then therefore going to be n squared, 3n, all over n plus 1, x to the 2n. So then, an plus 1 divided by an, well, this really should be limited as n approaches infinity, equals, this is going to be a bit messy, I apologize, n plus 2, x to the 2n. I'm going to take out 2 of the x's here, so I'm going to have x squared. All over, I'm going to write this as n squared times 1 plus 2 over n plus 1 over n squared times 3 to the n times 3. I'm going to rewrite this part up here as n times 1 plus 2 over n times, then I'm going to do n squared 3 to the n, n times 1 plus 1 over n times x to the 2n. Alright, so now we can do the canceling. So we have x to the 2n that goes away, 3 to the n that goes away, n squared that goes away, the n goes away. Since we're going to infinity, these all go to 0. And we're left with x squared over 3. And we want that to be less than 1. Therefore, x squared is less than 3. Therefore, x is less than square root of 3. Yes, and so they want the radius, you turn the radius of convergence. Yep. So they just want the radius convergence. Radius of convergence is square root of 3. So I know I went through that super fast, and I apologize. That's kind of how I approach the ratio test. And yeah, and then that would be pretty much the entire exam, or at least the second part for the non-calculator. Did the other part earlier. So yeah, that's how I'd approach it. Hopefully this would be a 5. I don't know, maybe. It kind of depends on how well you have to do. Depends on how well you need to do. So hope that helped. See you next time.